You're watching NASA astronauts testing equipment in the Neutral Buoyancy Lab at the Johnson Space Center. The lab, by the way, is also known as the world's largest indoor pool. There's a mock-up of the International Space Station in there.
All right, safety divers, I know that we're not on the best sound system today, so I'll just go ahead and set up again.
Astronauts train in the pool because underwater simulates the zero-gravity environment of space, and it's about as close as you can get to zero G on Earth.
Pick up different sizes of materials, anywhere like as small as like a 1 inch by 1 inch by 1 inch.
The tool being tested would allow astronauts to chip off and save samples of an asteroid while they are exploring its surface. Researchers want to study asteroids to learn more about the origin of the solar system. It's believed that asteroids have been floating around in space unchanged since the early days of the universe, and they could teach us a lot. However, researchers at NASA or some aerospace company did not invent this device.
So like our device, how it presses into like a surface, it has to be able to pick up off of a convex surface or a concave surface or a flat surface.
Okay, the DV1 has his light book on 3010.
To be able to chip a sample, take 3 samples without cross-contamination, and transport those back to Earth.
And one of these 2 handrails is great.
The tool, called a chip and ship, was designed and built by physics students at High Point University. It was entered into the space agency's Micro G Next challenge.
We worked with the astronauts. We have a really durable device. They were able to work it, fix it, move it around after we chipped the samples and were able to collect them. So it was a little scary at first because we weren't sure we were going to do it, but we talked them through it.
NASA set forth strict requirements for entries in the contest. The device could only weigh 15 pounds or less. It needed to be able to collect and isolate 5 samples from the asteroids. And astronauts must be able to manipulate the device in space, wearing bulky spacesuits.
And so we came up with this little ball valve down here where you can actually just kind of slide your hand up and down on it, open it and close it like this. It's a lot easier to move. You don't even have to squeeze your hand. You can just slide against it and press against it and it'll work.
So when you press it down, that's going to turn the thing on. That'll activate the drill?
Exactly. So once you turn the switch on, the hammer will actuate and it'll actuate the chip. So you wait till you're all the way down. So you'd have it off and then you need to turn it on. Drill, drill, drill. Turn it off. Collect your sample. Keep going.
The chip and ship is designed to capture and scoop up pieces of rock that are kicked up by the drill. The drill, by the way, is made of hardened steel. The rest of the device is aluminum.
So when you're going to the surface of an asteroid or a planet, you're really not sure what rocks you're going to encounter. So when you have these larger rocks or these larger surfaces that don't have the little tiny pebbles that you're looking for, you need to create those. And how do you create those? Use a device like this. The collection blades open from the side here, and that exposes here on the bottom the chipping chisel that will go on and chip the surface of the asteroid. And then when the astronaut feels that he's chipped a sufficient amount of rock, he'll gently pick up from the handle of the device, and that will close the collection shells, allowing the containment of whatever particles or rock chips that are floating around the surface.
And keeping that bulky spacesuit in mind, students designed each sampling chamber to be easily removed and replaced. The rings are for tethers, so nothing floats away in space.
If I could summarize this project experience in one word, it would be perseverance. Nothing ever works the way you think it will the first time. You might account for every possible thing you think can go wrong, and it's that one last thing you haven't thought about that goes wrong. So we did a lot of testing.
And that testing included the university's geology lab.
We actually went into the geology lab next door, and they have a giant collection of rocks, different types, and we found the type of rock that most closely mimicked that of an asteroid surface. So we took the rock out back and used that with our drill to drill into to see if we could get any chunks to come off.
The team spent almost a year building and refining their design, as well as the testing protocol, spacewalking guidelines, and a presentation for a NASA safety board.
We definitely spent a lot of hours working on stuff throughout the whole process, but it was definitely rewarding to see.
The agency was impressed, and the design could find its way into future NASA tools.
We had a safety review board, and when they first saw our device, their faces lit up. They really enjoyed seeing how our device worked.